Hello, this is Samantha Santillana, Communications Specialist for VICTREX USA. Welcome to our webinar today, Sealed to Survive the Extremes. Our speaker, Rich Leibfried, is Manager of Technical Sales and Marketing for VICTREX USA. Rich obtained his bachelor's degree in Polymer Science from Penn State University and is currently based in America's headquarters office in Conshohocken, Pennsylvania.
Thank you, Samantha. Today I'd like to share some of the experiences of the VICTREX team who have worked in the field to solve challenging mechanical and fluid engineering problems. I'll start with a brief introduction to VICTREX for those who may be learning about us for the first time. Then I'll move on to some current market trends and industry challenges because we know that operating environments will continue to change and OEM equipment will keep evolving to offer increased efficiencies while pushing for high quality and reliability. This of course means the design parameters will continue to change and drive the need for higher performing materials. Next, we'd like to provide a few high-level examples of VICTREX PEEK's proven performance that has translated into real value for our customers. Over a period of 30 years, this proven performance has literally set the standard for equipment ratings in some long-standing applications. Moving on from there, I'll explain the basics of PEEK as a semi-crystalline thermoplastic and go into greater detail about typical operating ranges and key engineering requirements for extreme sealing. I will cover some very important material property considerations for polyaryl ether ketones that every design and process engineer should know to ensure they are getting the most out of our material in a finished component. I'll also share some results from long-term performance testing on VICTREX PEEK that help explain how standardized properties like tensile yield strength and creep may or may not translate directly into application-specific performance for sealing components. After that, I'll share some success stories. The purpose here is to highlight common sealing applications for PEEK with the customer's requirements and the benefits they realize by specifying VICTREX PEEK. Finally, we want to highlight our VICTREX technical support capabilities that have evolved with our customers' needs. VICTREX continues to invest in resources to help our customers solve challenging problems, and we stand behind our commitment to be a solution provider. VICTREX is the world leader in PEEK polymer solutions with more than 35 years of PEEK polymer innovation to build on. VICTREX was founded in a management buyout from ICI in 1993. ICI had invented PEEK polymer in 1978 and created the VICTREX PEEK brand name and this product line, including the IP and patents, technology, processing know-how, and manufacturing facilities were carried forward by VICTREX Limited. VICTREX plc then became publicly traded through an initial public offering on the London Stock Exchange in 1995. Global headquarters and all manufacturing facilities are based in the UK, with 4,250 metric tons of production capability. Additional capacity of 2,900 tons is planned to come online in 2015. Besides the VICTREX Technology Center located at our UK headquarters, VICTREX has established global technology centers in Shanghai and Tokyo. We employ 650 people in 30 countries to serve the needs of our diverse customer base. Here's a one-page overview of the VICTREX product portfolio. It all started with VICTREX PEEK resin in the form of pellets for molding and extrusion. Over the past 10 years, we've forward integrated into semi-finished product forms including APTIV film. Our thin film extrusion line in the UK is dedicated to producing the highest quality PEEK films available from 6 to 750 microns. Bicoat coatings, fine polymers for electrostatic spray or aqueous dispersion coatings. VICTREX pipes, offering close tolerance OD/ID pipes and tubes for applications in aerospace, oil and gas, and in the industrial markets. VICTREX PEEK-based composites, providing fine powders used as a resin matrix in continuous fiber reinforced prepregs. Combined, VICTREX has developed over 800 commercial grades of VICTREX PEEK polymer, including pellets, powders, pipes, tubes, coatings, and APTIV films. Along with our product comes what we like to call value beyond the polymer. For example, VICTREX maintains and builds on the most extensive database of technical and application testing for PEEK. To aid in application development, we offer product samples, part prototyping, and mold trial support. Our customer service quotes 7-day delivery for standard products worldwide, and our logistics team plans for 3 months product inventory on hand in warehouses globally. Now that you have an inside view of Victrex, let's take a look outside to the industries we serve, specifically the industries that have a need for seals that can survive the extremes. I'll start with this overview of trends and challenges facing the oil and gas industry. Global consumption and demand continue to rise with finite resources. Enhanced oil recovery methods enable increased recovery from conventional reserves. Operating in more extreme environments requires technical innovation. The ability to withstand higher temperatures and pressures unlocks vast unconventional resources. Exploration and production costs are rising, driving the need for maximized efficiency. Service companies are pushing for high-quality, real-time data transmission and robust tooling to maximize production. The global community requires safe and reliable oil and gas operations. Environmental and government legislations are requiring increased quality and safety regulations. The oil and gas industry trends can be boiled down to four main challenges shown here: escalating demands, operational efficiency, reliability and predictability, and enabling innovation. Addressing these industry changes is our goal, so Victrex aims to support extended exploration to find the oil, and then boost and optimize production to get all the oil out of the ground quickly and safely. Now let's take a look at how this relates to sealing for the extremes. This slide provides an overview of the downhole tools used for oil and gas exploration and production, from seismic sensing and logging to drilling, then completion of the well to commence production. When production slows, stimulation tools can help enhance recovery by drawing more oil and gas out of the reservoir. Hydraulic fracturing, or fracking, is an example of well stimulation that has greatly enhanced recovery of natural gas. The key point here is that seal backups and connectors, which have a sealing function, are key components across many types of exploration and production tools. VICTREX PEEK has been specified in these applications for many years, and more extreme environments are driving new specifications into each new generation of downhole tools. Here we see a simple chart to show the typical HPHT operating environment for an oil and gas well. The arrows are meant to convey two things. First, the typical well environments are getting hotter, with higher pressures, so the HPHT range is expanding to what some call extreme or ultra HPHT. New temperature and pressure targets are being defined and are driving new polymer development. Second, PEEK is known to perform well with continuous operation in this range, but can also handle limited durations at higher temperatures or pressures. So the trends and challenges for oil and gas clearly show a growing demand for extreme sealing solutions. However, I would like to take a moment to show the value that has already been delivered with VICTREX PEEK. Proven performance in the most extreme oil field environments. PEEK's operating temperature range of -60 to 260 C with a pressure rating of up to 30,000 psi, and it withstands a wide variety of oil and gas fluids and sour gas exposure. Provides 100% greater pressure handling capability than PTFE and 300 times more creep resistance. PEEK has 12 times the compressive strength versus PTFE at elevated temperatures and pressures. Its compressive creep is 3 to 4 times less than PPS at 80 degrees C, more than twice the performance life. In multi-material sealing assemblies, VICTREX PEEK backup rings bridge extrusion gaps, and in connectors, VICTREX PEEK reduces the heat aging effect and extends the usable life. No electrical leakage. In connectors, VICTREX PEEK accommodates thermal expansion of metal elements, and the molding of integrated assemblies eliminates cracking and leaking to ground. We have some examples of extreme sealing in industrial environments, but I will cover these later when we focus on application success stories. Let's move now to the technical portion of this webinar, where we cover sealing engineering requirements and VICTREX PEEK material considerations in more detail. In this section, we'll talk about extreme sealing solutions, including key engineering requirements, material property considerations with PAEK polymers, and VICTREX PEEK long-term performance. Many of the key engineering requirements for backup seals are supported by the semi-crystalline nature of PEEK, which allow it to operate in extreme temperatures, chemicals, and pressures. This allows for reduced downtime and longer time between maintenance cycles, as well as increased productivity. The chemical resistance of PEEK gives it resistance to all common solvents, high and low pHs, steam, hydrolysis, and so on. This allows the use and inventory of fewer part numbers, and allows the same part to be used in a broad range of environments. The wear and abrasion resistance of PEEK allow it to be used in replaceable components for abrasion resistance. It extends the maintenance cycles and equipment life, and also allows long-term performance in abrasive oil field slurries. Backup seals also need to operate in a broad range of operating temperatures and conditions, from low to high temperatures requiring creep resistance or no cold flow, high tensile strength to bridge extrusion gaps, and high compressive strength to support high pressure differentials. Downhole oil field service at 500 Fahrenheit is typical for high pressure and high temperature operation, and the material still needs to be strong and stiff to bridge extrusion gaps. The use of fiber reinforced grades can add to the strength and stiffness of the material, as well as adding either thermal insulation or thermal conductivity if those are required. VICTREX PEEK might be best known as a high temperature material, but its combination of properties are what allow it to be specified in a wide variety of applications. Whether it's mechanical properties like creep, fatigue, strength, or modulus, its moisture resistance or hydrolysis resistance, its wear and friction properties or chemical resistance, it typically takes at least 2 of the properties listed on this page, but preferably 3, before any other material is eliminated. If there is only 1 or 2 of these properties required, there are typically other solutions existing. The VICTREX portfolio is mainly composed of our PEEK polymer. However, we do have HT and ST polymers, a wide variety of compounds including glass and carbon fiber reinforced grades, tribology grades for wear and friction applications, HMF grades, which are carbon fiber reinforced products with superior mechanical properties, higher than our standard chopped carbon fiber products, as well as our WG grades, which are proprietary PTFE blends for high temperature wear resistance. PEEK, or polyaryl ether-ether ketone, is available in 6 different viscosity grades, ranging from our ultra high flow 90 series to our general purpose 450 range, as well as the extra tough 650 range. These are all available in granule or pellet form, powder or fine powder, have a glass transition temperature of 143 C and a melt temperature of 343 C, an HDT of 152 C when unfilled, and up to 349 C when filled. Our HT polymer, or polyaryl ether ketone, or PEK, is available in 2 different viscosity grades, granules or pellets, powder and fine powder forms, has a glass transition temperature of 154 C and a melt temperature of 374 C, an HDT of 165 when unfilled, and up to 368 C when filled with reinforcing materials. Our ST polymer, or polyaryl ether ketone, or PEK-EKK, is available in 1 viscosity grade, has a glass transition temperature of 164 C, a melt temperature of 384 C, an HDT of 175 C when unfilled, and up to 383 C when filled. This plot illustrates the difference in the glass transition temperatures of our PEEK, HT, and ST polymers. The curves are measured on a DMTA, or Dynamic Mechanical Thermal Analysis machine. The glass transition temperature is a range over which the material softens into a viscous liquid or a rubbery phase. Amorphous materials typically just get more and more fluid above their glass transition, while semicrystalline materials like PEEK, HT, and ST will maintain mechanical properties and stiffness above the glass transition all the way to their melting temperature. If you take a horizontal line starting at a specific modulus and go across the temperature range, you can see how the materials differ and how much additional strength and stiffness is retained when you get above the glass transition temperature for the different materials we have. And this table is just a recap of the thermal properties of each of the different grades, including glass transition, melt temperature, HDT, filled and unfilled for each of the different base resins. It also shows that each of these have a similar level of crystallinity, and beyond what's on the table. Mechanical properties, for example, tensile strength and modulus, are all very similar, as well as the chemical resistance of each of these grades is also very similar. This slide shows how plastics can be categorized into commodity, engineering commodity thermoplastics, and high-performance engineering thermoplastics, PEEK falling into the high-performance category. On the right-hand side, you can see the top of the Polymer Pyramid, with amorphous materials on the left-hand side and crystalline or semi-crystalline on the right-hand side. At the top of the amorphous materials are the thermoset polyimides, which are best known for high strength and temperature resistance, but having poor processing capabilities as well as poor hydrolysis resistance. And generally, amorphous materials are known for their good dimensional control and low shrink, as well as isotropic properties, their transparency, but for having relatively poor viscosity for processing and poor chemical resistance and stress cracking. The semi-crystalline materials, like PEEK, are best known for mechanical properties including creep and fatigue, excellent chemical resistance and stress cracking, wear resistance, and excellent flow during injection molding or extrusion, but can be subject to anisotropy and high shrink. On the next few slides, we'll go through some background information on the differences between amorphous and semi-crystalline materials. On the left-hand side, you can see an illustration of the random orientation of the polymer molecular chains within an amorphous matrix. On the right-hand side, you can also see the base amorphous matrix, but it also contains some crystalline regions within there that are oriented and aligned. Those crystalline regions act as reinforcing structures within the amorphous matrix and give the polymer some additional properties beyond what you'd see with amorphous materials, including mechanical properties like creep and fatigue, and chemical resistance. Again, semi-crystalline polymers are composed of an amorphous matrix with crystalline structures that act as reinforcements within the matrix. For unfilled polymers, the mechanical properties above the glass transition temperature are controlled by the crystalline phase. For amorphous materials, there's no crystalline phase, so there are very little in terms of mechanical properties above the glass transition. The crystalline regions within a semi-crystalline polymer act to enhance their mechanical properties, just like you see with the addition of reinforcing fillers like glass or carbon fibers that help to increase strength and stiffness. If we take VICTREX PEEK 450G as an example, it contains 30 to 35% crystalline material within its structure, which is higher than most other PEEKs available on the market. This crystallinity influences properties like mechanical properties, including strength, stiffness, and toughness, long-term dimensional stability, like creep, and chemical resistance. It's also important to remember that crystallinity influences properties at elevated temperatures, even more so than at room temperature. Differences in the PEEK polymer structure, specifically the crystallinity, will affect the high temperature performance. Experienced processors and technical support from the resin supplier can help aid in successful applications of PEEK in more demanding HPHT conditions. The different versions of PEEK available on the market will exhibit different mechanical properties. For example, our VICTREX PEEK 450G, our unfilled general purpose grade, is strong and stiff. It has high tensile modulus, a high tensile yield strength, as well as a high elongation. Other PEEKs show lower yield strength at room temperature due to their lower crystallinity than 450G. However, this does relate to a higher ductility. The difference in PEEK materials can be referred to as a stiffness-toughness balance. In order to get stiffness, you have to compromise toughness, and vice versa. To increase toughness, you have to compromise stiffness. And this is due to differences in the polymer structure that affect factors such as the crystallization rate and overall crystallinity. This elevated temperature stress-strain curve also illustrates the stiffness-toughness trade-off. A higher ductility version of PEEK means it has lower crystallinity and lower tensile strength, especially at room temperature, but even more so at temperatures above the glass transition. Annealing, or heat treating a semi-crystalline polymer above its glass transition temperature, can increase the amount of crystallinity present. This results in less residual stress, higher mechanical properties, and better dimensional control. You can see this on a DSC trace of the annealed sample as an endotherm roughly 20 degrees C higher than the annealing temperature. A typical annealing cycle for PAEK materials contains a hold at 200 degrees C for approximately 400 hours. Annealing at higher temperatures will show a greater increase in crystallinity with a significant effect on the mechanical properties. Longer annealing times will further increase the level of crystallinity. This plot shows how the mechanical performance of PEEK can be enhanced with annealing. You'll see a slight increase in the tensile strength when annealing occurs below the application temperature, but a significant improvement when the annealing occurs above the application temperature. In this case, you see approximately a 90% increase in the tensile strength when tested at 275 C, when annealing occurs at 300 C for 1 week. Without looking too closely at the specific numbers on this table, you can see that crystallinity increases in PEEK, HT, and ST as you go from an as-molded condition to annealed for 1 day at 250 C to annealed for 7 days at 300 C. More importantly, you can see that the additional crystallinity present in PEEK 450G gives it less creep than other PEEKs at 200 C. However, with high temperature annealing, 450G's creep resistance is vastly improved and between 1/2 and 1/3 that of unannealed PEEK. The illustrations on this slide show how crystallinity and creep relate to backup seals. PEEK backup rings support high differential pressures and elevated temperatures to prevent the failure of elastomeric seals by extrusion. In summary, crystallinity is critical. High levels of crystallinity result in increased strength and stiffness at elevated temperatures, a significant improvement in creep resistance, as well as improved chemical resistance and higher compressive strength and modulus. Finally, I'd like to go through some application success stories, as well as talk about our VICTREX technical support capabilities. We have a number of successful applications in seals, backup rings, and packings. Effective sealing is a critical requirement throughout the oil production process. Some of the benefits of PEEK are design freedom with process versatility and ease of machining. Some of the key engineering requirements for these seals are differential pressure resistance from 20 to 50,000 psi, temperature resistance to 250 C and greater, high shear and compressive strength, creep and extrusion resistance, excellent chemical resistance, and ductility for assembly. And these are typically replacing or backing up and reinforcing elastomers and fluoropolymers. Downhole electrical connectors also perform in a sealing capacity. They're utilized for both the transmission of power and data between the operating environment and the surface. The benefits of PEEK include its ease of assembly. There's no impact from differential thermal expansion, and this is typically resulting in a loss of electrical insulation in traditional materials, usually caused by the thermal expansion differences and the gap that occurs between the conductor and insulator. The overmolding of PEEK on the conductors gives a durable seal that prevents the loss of electrical properties. Some of the key engineering requirements are electrical insulation, differential pressures of 20 to 50,000 psi, temperature resistance to 250 degrees C and greater, chemical resistance to downhole corrosive chemicals, moisture and hydrolysis resistance, and these are typically replacing glass-sealed ceramic, epoxy, or metal composite connectors. Another common application for PEEK is in valve seats. Seats are used in many types of valves for downhole tools, wellhead equipment, and refining processes. This specific example shows a ball valve. Some of the benefits of PEEK are its longer lifetime, its contribution to a lower total system cost, and its reduced wear and risk of damage. Some of the key engineering requirements are chemical resistance to a wide range of chemicals and environments, HPHT resistance, and a low coefficient of friction. PEEK seats are typically replacing either PTFE or corrosion-resistant alloys. Another application are composite wear rings made with VICTREX PEEK Polymer. These are high wear, high maintenance rings that are in pumps, traditionally made from bronze, stainless steel, and cast iron. And the benefits of PEEK are its low friction and wear, the ability to have lower and reduced running clearances, its superior strength and stiffness. It's a non-galling material and also non-seizing, and offers an efficiency gain of 4 to 5% at a 50% reduction in clearance. This application is for a valve seat for a natural gas pressure regulator in a valve that's used in natural gas fueled vehicles. This is replacing a metal valve seat that leaked due to deformation of the seat. Some of the benefits of PEEK are its operation at high pressures across a wide temperature range, its ability to withstand cyclic loading and fatigue, and its operation inside a compressed natural gas tank. There was no deformation of the PEEK and no leakage after its replacement of the metal seat. This application uses our APTIV PEEK film as a diaphragm liner for a back pressure regulator. The problem with the PTFE material was migration of the existing liner, blocking the flow to the port, and that was due to the poor creep resistance of the PTFE. The APTIV PEEK film is acting as a backup seal for the PTFE diaphragm and provides excellent high temperature creep resistance, excellent barrier properties, the ability to use it up to 260 C, excellent moisture resistance, and broad chemical resistance. It also allows no cold flow of the liner in acting as a backup. VICTREX is dedicated to PAEK materials and technology. Our technical service and support for customers and OEMs is industry focused. We can help you to identify the correct grade for your application using our 35 years of experience with PEEK, but also with tools like FEA. We provide part and tool design assistance, including mold filling analyses. We provide direct manufacturing support, including molding trials and advice on annealing and finishing operations. We also have regional innovation and technology centers that provide application development support. If you ever have any questions about VICTREX PEEK, call us anytime. In summary, VICTREX has more than 30 years experience in sealing applications. We have a passion for customer support with convenient global logistics for fast shipments of raw material and samples. We have innovative solution experts with technical support available in 30 countries, supplemented by our own testing facilities, and proven performance in mechanical sealing and electrical integrity underpin 30 years of success in the industry. Thank you for your time.
We have a limited time now for question and answer, but any questions submitted will be answered by our experts via email after the webinar. Rich, here's the first question. How do you decide when to go with reinforced PEEK, glass or carbon filled, versus unfilled PEEK in a sealed backup ring?
That's a great question. You really need to look at the key engineering requirements, VICTREX calls these KERs, to perform as needed in the end-use application. This means considering the environmental requirements like continuous exposure to high temperature, chemicals, and wear. You also need to consider static and dynamic loading, as many seals will experience fatigue due to thermal or load cycling. Finally, you need to establish the expected design life for the seal and consider the effects of creep. VICTREX has the world's most extensive PEEK testing database, and our technical team leverages that database to help you select the best VICTREX PEEK grades to meet your requirements. Obviously, end-use testing is always recommended for the part designer to confirm that VICTREX PEEK is suitable for the application and finalize the material selection.
All right, I have our next question here. Are there any special machining considerations for PEEK?
In general, VICTREX PEEK is considered easy to machine with proper tooling and CNC equipment for rigid thermoplastics. Unfilled PEEK has inherent high surface hardness and toughness compared to other engineering polymers. Glass and carbon fillers increase the hardness of the PEEK compound, and tensile strengths can exceed that of aluminum. For this reason, diamond or PCD-coated inserts provide the best results for single-point machining where extensive turning is needed. Carbide tooling alone is not recommended for turning, as it will dull quickly and result in poor surface finish and material pullout that appears as pitting. The VICTREX technical team can help you with more detailed machining guidelines.
Okay, our third question. What is the most common failure mode for PEEK in seal rings?
We get this question often, and in our experience with thousands of sealing applications, It's rare to see catastrophic failures with VICTREX PEEK seals. However, a few of the failure modes we do see in rotating seals are excessive wear when high pressure or velocity take the material beyond suggested PV limits. In some cases, this is resolved by re-evaluating the best VICTREX PEEK grade to use in the application. For example, our new VICTREX WG series offers higher PV limits and extends performance life over standard PEEK bearing grades. For static seal backup rings, there are some cases where PEEK is pushed beyond its limit for time and temperature, causing it to creep out of position. This is usually addressed with a regular maintenance and scheduled replacement of the seal before a leak can develop. Here, the seal designer may then specify a reinforced grade, which has much greater creep resistance to extend the design life or even eliminate the need for replacement.
Okay, it looks like we're out of time. To listen again or to share this webinar, it will be available on demand in a few days. I'd like to thank everyone for their time to listen in today, and a special thank you to Rich Livefree for presenting.